All right, so what we're looking at here is higher order derivatives. We're going to look at motion specifically, so we're going to talk about distance and velocity and acceleration. And so this kind of ties in for those of you who are in my physics class, to be honest with you. It's kind of looking towards university physics, where you're going to use derivatives. And so to start off, let S of t represent any distance function where t is represented in time. And the reason we use s is because when you're taking the derivative, you've got d, so we don't need a d function. All right, so then what you have is when you're talking about the rate of change of the distance with respect to time, which is the derivative of s of t, that's actually your velocity function. And when you take the double derivative, or the derivative of velocity, you get the acceleration function, because again, acceleration is the rate of change in the velocity with respect to time. And as I mentioned, is if you head to post-secondary physics, you'll actually look at what's called the jerk function, which represents a sudden jerk or change in acceleration with respect to time. And that would be the triple derivative. Now, we were not going to get into triple derivatives, but that's just a little side note on that. All right, so if we take the derivative of our distance function, you get velocity. You take the derivative velocity function, you get the acceleration function. That's our focus. All right, so we have example 1, where it says a drag race car's position from the starting line is given by that equation right there. Find the velocity and acceleration as functions of t. All right, so we have our s of t function. But again, if I find the derivative of s of t, the change in distance with respect to time, that's actually going to be our velocity function. And in this case, you're going to use my power rule. This is just a simple polynomial, and so 3 times 2, I'm going to have 6. Subtract 1 from the exponent, and I get 6t squared. And then the derivative of 36t is just going to be 36. And of course, the derivative of negative 10 is just 0. But then if I find the change in velocity with respect to time, so the derivative of vt, that's actually our acceleration function, a of t. All right, and so if I take the derivative of my velocity function, again, just using the power rule here, 2 times 6 is 12. Subtract 1 from the exponent, and so the derivative is just 12t. There we go. All right, now let's try something a little bit different, or not completely different. A water rocket is shot upward with or at an angle. The height function s of t in meters of the rocket above the ground is s of t, and there's our equation where t is in seconds. Determine the maximum height reached by the rocket. And so what happens here is, for the max t, we have, let's see here, for max t, for the max, sorry, we have our s prime of t is going to be equal to 0, because that is when our velocity is equal to 0. Because at your highest moment, and this is something for those of you in my physics class that helps out, is that at your highest point, your velocity is 0. Because all the time your velocity has a positive number on the way up, but it's decreasing, and then when it gets to the very top, your velocity is 0, and after that your velocity starts heading downwards. So it's actually increasing but becoming negative because it's headed downwards. And so if I find the derivative of s of t, so let's find that derivative. Again, I'm just going to use the power law. And so 2 times negative 5, we're going to have a negative 10 t, and then the derivative of 30t is just 30. And now I'm going to let s of t, or the s prime of t, equals 0. And then I'm going to have to solve this equation. So I'm setting my velocity equal to 0. And let's see here. I move that negative 10t over to the other side. I get 10t. All right, and then I'm going to divide both sides here by 10. And, well, t is equal to 3. But that's just telling me the time at which we've reached the maximum height. That's not telling me the maximum height. So I'm going to have to sub this value back in to our original equation, because our original equation tells us the height of the rocket. And so now I can find s of 3. So I'm back into the original function, as I've said. And so I'm going to have negative 5, 3 squared. Let's see, I got to make this smaller writing so I can fit everything in there. There we go. All right, plus 30 times 3. And I can't forget my little plus 1 there. All right, so let's see here. Bedmas. We have 3 squared is 9 times negative 5 is minus 45. And then, well, plus 90 and then plus 1. And let's see, if I add those two together, or add and subtract those two together, figure them all out, I end up with, let's see here, negative 45 plus 90 is 45. Add 1, we get 46 meters is our maximum height. So I had to use both the velocity function, which is the derivative of our distance function, and the distance function for that one. I believe there's a part C here. Oh, part B. All right. Part B, determine the velocity of the rocket when it is 1 meter above the ground. All right, so again, I don't know when it's 1 meter above the ground, so I'm going to have to find that out first. So I'm going to sub 1 in for s of t. So I have a height of 1, and so therefore I've got, so this is a nice way of saying s of t equals 1. And we're going to find the t. All right, so I've got 1 is equal to that negative 5t squared plus 30t plus 1. All right, so now I need to solve this. This is a quadratic equation. First thing I'm going to do is I'm going to move this 1 over to this side. Because to solve a quadratic equation, whether you're going to do factoring in the quadratic form, you always have to have a 0 on one side. And what happens there is nothing's over on this side. I still have my negative 5t squared plus 30t. Now I have a 1 over here, but when this one comes over, it subtracts it. So then I've got nothing for my numbers. Now, I want to solve this quadratic equation. Well, I could go by factoring. They each have a factor of t in there, so I could factor out a t. And so now I have negative 5t plus 30. All right, now solving each piece. Well, this piece here, t equals 0. So that's at the start when the velocity, looks like this rocket starts 1 meter above the ground. All right, and then the other time, let's see here, I'm going to have to solve when we have negative 5t plus 30 equals 0. And let's see here, move negative 5t over the side, divide both sides by 5. I'd get t equals 6. So I've got 2 times when the velocity is 1 meter above the ground, when it starts and at 6 seconds. And so it says determine the velocity, so I'm going to have to use my velocity function, which again was negative 10t plus 30, because again, the derivative of our distance function is velocity. All right, so I'm going to write that down here first, is that v of t, our velocity function, is equal to, whoops, forgot already, negative 10t plus 30. All right, negative 10t plus 30. So I'm going to have to substitute into this equation twice. All right, so let's see. The first time, I guess we'll go with the start. V of 0. Whoops. V of 0. Let's see. Well, I'm just going to put 0 in for t, so it looks like it's just going to be 30 meters per second. Wow. Okay, so this rocket's 1 meter above the ground at initial takeoff here. It's moving already. And then the next time, I got to find v of 6, which is going to be, let's see here, negative 10 times 6 plus 30. Oh. Well, this must be a toy rocket then, because this is going to be negative 30 meters per second. So one of these velocities means upward and one means downward. Again, the positive sign means upwards. And the negative sign means downwards. And for those of you, again, who've taken my physics class, we've gone through that several times, and will again, as we're moving towards forces, energy and forces. There we go. All right, so there's our velocity. All right, let's see here. What else we've got? Intervals. Let me try something a little tougher here. All right, so the position, again, that's a height or distance of an object moving on a straight line is s of t equals 6t squared minus t cubed, where s is in meters and t is in seconds. Good. Assume a positive direction is moving right and a negative direction is moving left. Determine the velocity and acceleration of the object at t equals 2 seconds. All right, well, the first thing I do is I have to come up with the velocity and the acceleration function. So I'm going to find the derivative of s of t, and again, that will be our velocity function. And let's see here. So again, finding the derivative, I have 12t, and then I'm going to have minus 3t squared. All right, now if I want to find the velocity at 2 seconds, I'm going to sub that value in to our velocity function here. So v of 2 is equal to, let's see here, 12 times 2 is 24, minus, again, it's, to follow Bedmas, t squared is 4, times 3 is 12. All right, so our velocity is looking like it's going to be 12 meters per second, and again, it's a positive number, so that's going to the right. All right, now acceleration. Acceleration would be the double derivative. So we put two little marks there, would be our acceleration function. Or it's a nice way of saying taking the derivative of our velocity function, which was 12t minus 3t squared. So our acceleration function is going to be 12t 12 minus 6t. Again, just taking the derivative of our velocity function. And so the acceleration of this object after 2 seconds, again substituting in a 2, for t I'd get 12 minus 12, which is just 0. Whoops. Equals 0. All right, so it's not changing its velocity at all. When your acceleration is 0, it means it's not changing. The velocity is not changing, again, because that's a rate of change. All right, and then it says, what direction is the object moving at t equals 5 seconds? Well, again, if I'm looking at what direction the object is moving, I need the velocity function. And so I'm going to, again, sub in 5 for the velocity function this time, not 2 like I did just up above. And so I got 12, let's see here, times 5, minus 3 times 5 squared. All right, so let's see here. 12 times 5, I know is 60. Then I'm going to do some Bedmas here. So let's see here. 5 squared is 25 times 3 is 75. And it looks like, whoops, we get minus 15, which means this velocity is going 15 meters per second but left. So the answer to the question is, which way is it moving? Well, it's moving left. All right, now. So C, it says, at what time is the object at rest? Which means at rest means it's not moving. So again, I'm going to use my velocity function, and I'm going to see when it is equal to 0. So I'm going to set v of t equal to 0, because that's when we're at rest. And so that function, we're going to have 12t minus 3 times t squared is equal to 0. All right, so again, I got a quadratic equation going on here. And so I'm going to, and I got a 0 on one side, which is the start of solving a quadratic, but I've got a t on both terms. And so I'm going to factor out a t. All right, so I'm going to have a 12 here and a minus 3t in the other section equals 0. And well, this one, just like before, is easy to solve. That's t equals 0. Well, at the start, this object's at rest. All right, and then down here, I can solve this second piece, where we got 12 minus 3t is equal to 0. All right, let's see. I move the 3t over to the, or negative 3t over to the other side. It's going to be a 3t. I'm going to divide both sides by 3 and end up with 4. 4 seconds. So at 0 and 4 seconds, the object has stopped. It hasn't moved. Now, that's going to tie in here because we get to D. Let's see, let's move this up. There we go. When is the object moving right? All right, now here's the thing. We're going to do a little table here, and this is something that's going to show up quite a bit in this course, just like it did in advanced functions, is that I know between 0 seconds, the start here, it's at rest. It's not moving at 0. And at 4 seconds, it's at rest as well. But in between, I don't know what's going on. Is it moving left or is it moving right? So I've got 0 is less than t is less than 4. And then I've got greater than t, or sorry, t is greater than 4, I should say. So I want to know what's going on in these intervals. So what, again, I can use is my velocity equation, which is right here. And I'm going to substitute a value in this interval, and that'll tell me whether this thing's moving left or right, because it can't change directions between, it's got to go to rest first. So my guess is, well, it could either go rest, moving right, rest, then keep moving right, or it could go right, left, or left, or left, right. So there's lots of scenarios here. So what I'm going to do is sub in, I'm going to try, let's see, t equals 3. Oops. All right, so I put a 3 in here. Let's see here. 12 times 3 is 36. Minus, and this is just a trial. You could try 1. That's probably would have been an easier number. Let's see here. So then t squared. I got 3 squared is 9. Times 3 is 27. So I get minus 27. So it is positive, which means on the interval 0 to 4, this object is moving right. But then it stops, and then after 4, I don't know. Does it keep going right, or does it switch to left? I don't know. We'll check it out. So I'll try t equals 5. I'll try out. All right, so again, actually, I think we did that one. Yeah, we did 5, and we got negative 15. There, that value helps. And so it's negative on this interval, and so the object goes left. And then it never stops after that. So it starts going right for 4 seconds, stops, and then goes left after that. All right, I got something else down here. Whoa. When does the object return to its initial position? All right, so that's a little bit different. So we're talking about position, and its initial position is 0. And so we want to now set just s of t, the position function, equal to 0. So when is it at 0? I'm assuming at the start. All right, and so our original function here is going to be set to 0. So I'm going to have 6t squared minus t cubed, is equal to 0. All right, so I'm going to have to solve this equation. Now, the first thing I'm going to do is factor out a t. Actually, I can factor out a t squared. They both have two t's involved, and so I'm going to have 6 just minus t here. And so I can now solve these two pieces. Well, when does t squared equal 0? No matter what, take the square root of both sides, it's at the start. T is equal to 0. And then over here, the second piece, 6 minus t equals 0. Well, I move negative t over to the other side, so it would become positive, and so t equals 6. So it's returning to its original position. Well, it starts at that original position, and then it's back there at 6 seconds. All right, and I think we got one more here describing the, describing the entire motion. It says draw a schematic line diagram to show the position of the object over a 7-second time period, including all extreme positions. All right, so let's see here. Well, in terms of drawing a line, let's go with purple here. So this is t equals 0. Starts right here. And then for 4 seconds, I know it moves to the right. All right, so for 4 seconds, it moves to the right. All right, so that's t equals 4. Now, how far did it get distance-wise? I don't know, but I'm going to substitute that into my original function there, s of 4. And I'm going to solve that. So see how far it went. Let's see here. I got my original function there of 6t squared minus t cubed, and when I sub in s equals 4, I get 32 meters. So that's a 32-meter distance. Okay, now it said it went left after that, right? Left after 4 seconds. But also I have the knowledge that at t equals 6 seconds, it got all the way back to the original position. So there's t equals 6 seconds. And then it kept going left. How far left at t equals 7? I don't know. I'm going to sub 7 into our distance function again. Let's see how far left of the position, because I want over a 7-second time frame here. And let's see here, 6 times 49, and then I get minus 7 cubed. All right, so I do that. I end up with minus 49 meters, which means 49 meters left. So this isn't really drawn to scale, but this is 49 meters from the original position. So in 1 second there, from 6 seconds to 7 seconds, it went 49 meters, 49 meters to the left. And again, that's just getting all that information from our derivatives. And again, your distance function, when you find the rate of change of distance with respect to time, you've got velocity. And when you find the derivative of velocity, which is the change in velocity with respect to time, that's acceleration.